Hi everyone. Today we're going to talk about how to solve differential equations, specifically first order equations using Euler's method. So, as you might recall, a first order equation is simply an equation of the form y prime equals stuff with x and stuff with y. We sort of signify a generic first order equation by writing y prime is equal to big f of x, y. Now, we've developed a number of techniques for solving these equations. We've talked about separable equations, exact equations, first order linear equations, and so forth. But sometimes there just aren't any good solutions to be found. At least not what we call closed solutions, solutions that have a nice formula to them. When we encounter situations like this, we have to resort to what's called numerical approximation. That is, rather than trying to find a formula that solves our equation exactly, what we're going to do is sort of describe points through which a solution is approximately near. Now, to do this with Euler's method, we've got to recall this idea from Calc 1. Imagine you're given a function, f of x, and you're given a point, x naught. You can draw a tangent line through that point. We spent an awful lot of time in Calc 1 doing this, didn't we? So there's my tangent line there in blue. And as we discussed in Calc 1, the equation of the tangent line at that point is just given by this equation, f prime of x naught times x minus x naught plus f of x naught. That's our equation of the line through the point x naught. And one of the facts we would sometimes reference in Calc 1 is what we would call linear approximation. The idea was that a given function, f of x, would be approximately equal to the equation of the tangent line, at least for x near x naught. And you can see that that's largely the case here in this diagram. When we're looking at x naughts that are near here, sure enough, the value of the function is very close to the value of the line. Of course, once you start to deviate from that, that difference becomes more severe. But as long as x is pretty close to x naught, this works. Now, the exact meaning of pretty close and near can be quantified in all sorts of ways, and there's a wonderful subject called numerical analysis that kind of goes into the nuts and bolts of this. But since this is just an intro to differential equations course, we're just going to say, as long as x is near x naught, this works. Now, how do we use this idea of linear approximation to solve a first order equation? It's a good question. What we're going to do is start with what are called initial conditions. So we'll be given initial conditions. And these initial conditions are basically just like any other initial condition problem. You'll be given a value x naught, y naught, a point through which we want a solution. To our first order equation. So you'll be given some initial conditions, a specific point x naught, y naught, and you'll want to find a solution that satisfies that differential equation and goes through that point. So here's the idea. We're going to pick a small value. Let's call it h. And what we're going to do is we're going to, I need some space here to draw this picture. So we're going to look at points that are distance h from each other, so forth. The idea here is that the distance between any two of these is just going to be h. And of course, like I said, we'll be given a point, initial point, x naught, y naught. Now, in Calc 1, you were oftentimes given the function and then told to sort of determine the equation of the tangent line. But one of the features of being given a differential equation like this one here is that although we may not have our function f of x, at least not a solution to the equation y equals f of x, we do know the slope of the tangent line. We can figure out the slope of the tangent line of a solution through this point. And so the idea is that, sure, let's imagine there is a tangent line here. And this tangent line is, in this case, instead of evaluating the derivative of some solution at the point x naught, we'll instead use the fact that our derivative is equal to this function. And so our L of x now will be given by this equation. That'll be our equation right there. And of course, the actual function, we're not entirely sure how it behaves because we don't have an explicit solution to our differential equation. Maybe it's like this. But that's okay. We don't know what it is exactly. But the idea now is that we can now pick an approximate point, a point that's pretty close to this. So if this is our point x naught, y naught, we could then construct this point here. And the idea here is that that green point is close. Sure helps to spell the word close correctly, doesn't it? There we go. Close to f of x1. The idea here again is h is small, and so when we approximate the true solution by evaluating at x1, we're getting something that's not exactly a point on our curve, but we're getting something that's pretty close to that point on the curve. And that point, we're going to call this y1. There we go. So this right here is the point x1, y1. Now if we want to figure out the equation for y1, it's not too hard to do. We're just computing it using that linear approximation. I'm just plugging x1 in to L. When I do, I get the following result. y1 is just going to be f of x naught, y naught times x1 minus x naught plus y naught. And again, it's important to remember right here, the distance between x1 and x naught is h. And so, in fact, this simplifies just a little bit more. You can write this as big F of x naught, y naught times h plus y naught. And this whole process can be repeated. We can move then from x naught. Again, it sure helps to spell correctly. Let's fix that. Still trying to figure out how to use this stylus here. There we go. We'll now sort of repeat for x1, y1. We'll sort of assume that our solution goes through x1, y1, or is at least close enough to it. and then find a new solution or a new point. Find a new point, x2, y2. If you want to see how this works in general, it's not too hard. The idea roughly is this. In general, you'll compute your yn coordinate by, maybe we'll call it yn plus 1 coordinate, by plugging f of x n yn times your h plus yn. And as long as you know what your big F is, you should be able to do this. And your xn plus 1, this is somewhat implicit in the setup we had already. It's just going to be this. It's going to be xn plus 1 equals xn plus h. And this method of constructing points, this is what we call Euler's method. Now, is it going to give us a good solution? Well, that sort of depends, doesn't it? It depends on what this function is. It depends on how small your h is. As a general rule, the smaller your h, the more accurate your solution will be. But again, the size of your h, however small it must be, is going to depend a lot upon the function you're working with, and even on the point you start at, what your x0, y0 is. There are a variety of ways of measuring this error. I alluded to that earlier when I talked about the field of numerical analysis. For now, we're not going to worry about it. We're just going to use this method as though it is accurate. Now, of course, one way to use Euler's method is to just go ahead and sort of recurse through all this. You know, it'd take quite a bit of work, but you could do it. You could maybe compute for x1 and y1 and x2 and y2, maybe all the way out to x5 and y5, but it gets kind of dull after a while. And so what I want to teach you to do today is to use Geogebra to help you do this computation. So give me a moment here. We're going to flip out of writing mode, and we are going to move to Geogebra Classic. Hold on, I'm going to make sure this thing is still recording. It is. Phew! Now, if you don't know about Geogebra, I should mention this. Notes for Euler's method can be found here at Paul's Notes. I really like them. They're very well written. You can follow the instruction there in case what I wrote didn't make sense. You can find it's all basically the same equations I had earlier. Geogebra, you can download this at geogebra.org, and if you click on app downloads, you'll see that they have a variety of applications we can use. You're going to want to use Geogebra Classic 6. You can download a copy onto your computer, which will probably be easier to use, or if you want to live on the wild side, you can try running an in-browser version of the app. So here's Geogebra once you boot it up. It looks kind of like Desmos, or sort of a generic graphing calculator system. One of the differences between Geogebra and Desmos is that, well, Geogebra has a lot of features. When I clicked on this menu here, I get a variety of tools, or what they call perspectives, for helping me do different types of math problems. We're going to mainly work with the graphing and the spreadsheet perspective. So let's go ahead and do that. First, probably be good to start off by giving a good example to illustrate Euler's method with. So let's write down an example here back on OneNote. Example. Let's consider this one. Y prime is equal to negative xy over square root of 1 plus x squared. You could solve this. You could solve this one by hand, and perhaps we'll do that momentarily to see whether we're getting a good approximation or not. But for now, let's just work with it. We'll think about this example. Now, on Geogebra, I'm going to record this function in my graphing calculator section. It's pretty easy to do. You just sort of mouse over to input here, type f of xy equals negative xy divided by square root of 1 plus x squared. Press enter. So it's stored right there. Another thing that would be good to have is a sort of h value. H of 0.1 seems about right to me. Let's try that. And we should probably have some initial conditions as well, shouldn't we? Let's write those down. Let's say x naught equals 0, y naught is equal to, I don't know, we'll say 1. That's a nice point to go through. Okay. Now, here's how we can have Geogebra perform Euler's method for us. What we're going to do is click back on this menu, and under Perspectives, go to Spreadsheet. Now we get a spreadsheet that's kind of like Excel. And what we're going to do is generate our x-coordinates. I take that first cell, A1, and do double quotes with x in there. And I'm going to start at my value x naught. It'll just be 0, won't it? And then I'm going to increment my x's, and in doing so, obtain a nice formula here for them. So if you've ever worked with Excel before, this should look a little familiar, but what I'm going to do is take my cell A2 and add my h value to it. When I do that, I'll get a 0.1 because h is 0.1, and when you add 0.1 to 0, you get 0.1. Now, one of the nice things you can do with Geogebra is grab that bottom corner there, that blue square, and pull it down. And what Geogebra will do is basically apply this increment to everything beneath it. This cell here is A3 plus h. This one is A4 plus h. Actually, I think I might have... Sometimes you can accidentally edit these things, so just be aware of that. And now I'm going to define my y-coordinates. This is where we have to start to use Euler's method in a bit more detail. So my initial point is y equals 1. But I should probably look back and think, all right, how are these y-coordinates produced? Let's take a look again. It looks like you take whatever your x1 or your xn and your yn is, plug them into your f, multiply by h, and then add yn. So I'm going to do that here on my spreadsheet. So I'm going to take f of whatever my x naught and my y naught were. In this case, my x naught is in column A, row 2. So I'll do A2, and then my y naught will be B2. Multiply it by h, and then add the y naught, or in this case the B2 that had come before. And in this case, we don't really have any change, do we? But as we move forward in time a bit more, we start to see that the y values change on us, albeit rather slowly. So just to reiterate, this equation is f of A2 B2 times h plus B2. And that really is, when you look back at this equation, that's what we're using here. So we're able to construct all these points here. Now, this is some nice information to have, but right now Geogebra doesn't really see these as points on the plane, so we kind of have to tell it that that's what we're going to do. So next we're going to take that point x naught and that point y naught, which are stored in A2 and B2, and put them there, 0.01. And you can see that point now just sort of popped up there, didn't it? And if I take this corner and I drag it down some more, you'll see that there's a lot more points that just sort of pop up. That's pretty neat, huh? Those are the points that Euler's method gives us. it might be a good idea to resize this a little. You can resize by clicking somewhere, probably on this gear here. Right, yeah, that's where it is. That gear, maybe we'll go to 2.5, -1 there for our y min, and a 2 for our y max. That looks a little bit cleaner. Let's see our points right there. And you kind of get an idea that that might be the shape of your solution. Now, one of the nice things we can do on Geogebra is actually sort of draw a polygonal line through all these points. We just need to remember which points these are in the spreadsheet. We begin with the point C2 and end with the point C24. So we're going to change perspective again. We're going to go to graphing, and we will enter in polyline. I want to start with C2, go to C25. I don't know if you can tell, but now we have a few more points in there, a few more little lines there connecting them all. Now, one of the interesting things about Geogebra is that we can adjust the h value live. We don't want to let h go negative, though. You can see it kind of flipped over to the other side when I did that. Let's make sure that doesn't happen. Let's go to slider here. We'll go with 0 to 1 with an increment of 0.01. That looks good to me. That'll allow us to sort of see how the shape of this changes as we increment h. This is a pretty steady solution, all things considered. It looks like the shape hardly changes at all with the h you're using. You can tell that I can go further to the right in my approximation when I have h larger. Obviously, not all my points are clustering together, but we should be getting greater accuracy when we solve this way. And so that's how you can get a good approximation and a nice plot to an approximate solution using Euler's method. So let's compare this against the real thing. Let's go back and see if we can solve this example symbolically. For your project, you won't be able to do that. It's not going to be so easy to do this. But for this one, we should be okay. So this looks like a separable equation, right? We can write this as y prime over y equals -x over square root of 1 plus x squared. And if we take the antiderivative of both sides with respect to x, we should get natural log absolute value of y is equal to, and I might be rushing it a little bit here, but the idea is that if you worked out a u substitution here, if you let your u equal 1 plus x squared, I kind of went through all the details. I'm not going to go through them all, but you can check. You should have square root of 1 plus x squared here, and you take the derivative, right? You can think of this as 1 plus x squared to the 1/2, right? The 1/2 will come down, but it'll cancel via the chain rule when we differentiate 1 plus x squared, and that 2 comes down. So just have a negative there. Plus some constant, I'll call it C1. This should look a little familiar to you, by the way. We did this problem in our first worksheet of the course. So if you feel a little tripped up on this, go back and look there. You can find the solution. But what we should get when we make each of these exponents the exponential function is e to the negative. I was having trouble getting my stylus to draw there for a second. Times that. I forgot about the e to the c1, didn't I? And I forgot about the fact that this is really here. Let me just edit this a little. There we go. We're really just saying absolute value of y is equal to that, aren't we? But then, when we drop the absolute values, we will find that this is a constant times e to the negative 1 plus x squared, where our c is just plus or minus e to the c1. There we go. That looks good. And of course, we want to find the solution that goes through the point. We want to basically solve for solution through the point. X dot y naught is equal to 0, 1. So we'll plug 0 into this equation. When we plug 0 in, we'll get c times e to the negative, well, plug 0 in there, you'll get e to the negative 1, right? And we'll want this to equal 1. So that tells us our c is equal to e. And thus, our solution to our equation, so let's look back there for a second, it's going to be y e times e to the square root of 1 plus x squared. Or if you want to write it in a less weird way, you can write that as 1 plus x squared plus 1. And that is our solution. So let's compare real quick, see how Euler's method did at approximating this solution. So we will type in e to the square root of 1 plus x squared plus 1. And apparently that's not how you do it on Geogebra. So we'll try this way. And it doesn't like that either. Let's try g of x here. Does it like e to the x? No, of course not. Does it like the exponential function? No, it doesn't like that either. I wonder how you do this thing. Somewhere that function showed up. There it is. Oh, look, it can do exponential. I knew it. You know, I have a feeling I screwed up somewhere. I bet you I lost a minus sign. That's exactly what happened right there. I lost it. You viewers at home, you probably caught that. I didn't. Good for you. Let's fix that. I want you to know, you better not be on Facebook or anything like that right now. I know this may not be the most entertaining thing ever, but it's still important. I mean, look at that. That's beautiful. Do you see that approximation? You can tell when h is large, it's not quite as good all the time, is it? It's a little off there. But when h gets small, man, that approximation, it's spot on. It's looking really good. It looks like I lost my polyline somewhere. Let's put that back in. There we go. How do I do this? I press enter. I feel like this color is wrong. What about you? Wonder how you change the color on this. Maybe you go to settings. There it is, color. We'll go for a nice purple color there. Darker. There, now you can see it. Okay, so that's that, folks. Now for your project, of course, you're going to be modeling the spread of the now very popular coronavirus using the SIR model. And in that case, you will be working with 3 Euler method approximations. And so to do that, you're going to have a somewhat more complex spreadsheet here. You'll ultimately have 3 columns of points. But you should be able to do it, and of course I'll be around in case you have questions. So that's it for today. I hope you enjoyed this video. Please share with me anything that you feel should be improved. I've never taught via internet video before, so I have a lot to learn, and I appreciate whatever feedback you can give me. Alright, that's it for today. I'll see you guys later. Bye.